Okay, welcome back, everyone. I'll just remind you where we were at. We're in the course of studying the diameter of the mean field minimum spanning tree. So just a quick recap of where we got to last lecture. So the setting last lecture and throughout this one is the complete graph with IID uniform 0, 1 edge weights. And then we wrote MSTN for the resulting minimum spanning tree. Right, and then we defined FNP to be the forest, which was the minimum spanning forest of GNP. So if you like that, right, this is what this is the forest built by Kruskal's algorithm coupled to the Addario-Berry graph process. And then our goal is to prove that the diameter of this minimum spanning tree is of order n to the third in probability. So what we'd seen so far is that so I'm going to give myself a bit of notation, which I didn't use last lecture, but which I'll use quite a bit today. So if I write H epsilon for the largest connected component of the graph, Gn 1 plus epsilon over n, and T epsilon for its minimum spanning tree. Right, so this is, this is the component of the minimum spanning forest, which has the same vertex set as H epsilon, right? So this is going to be a subtree of the eventual minimum spanning tree. Then we saw that if epsilon is 0, so that's in just the perfectly critical random graph Gn 1 over n, then we saw a lower bound on the diameter. So the probability that the diameter of the minimum spanning tree is small, say at most n to the third over k. Well, that's at most. In order for the minimum spanning tree to be small, the tree T0 has to be small because that's a subtree of the minimum spanning tree. So that's at most the probability the diameter of T0 is at most n to the third over k. And that's less than delta, right? Where for this bound, we used our understanding of the structure of a critical random graph as roughly speaking, a sort of something that looks quite a bit like a tree of size of order n to the 2/3 with a small number, a bounded in probability number of surplus edges. Okay, and then also, I'd left you with a way to start to think about upper bounds on the diameter of T0 in terms of the diameter of the corresponding component of the critical random graph. So that was this exercise that said that if I take some graph H and add an edge UV to it, then that can't cause the diameter basically to go down by more than a factor 2. Okay, so using that, you can prove that just by repeatedly applying that, thinking about deleting a sequence of edges. So, if H has surplus S and T is a spanning tree of S, then the diameter of the tree is less than, say, 3 to the s times the diameter of the graph. Okay, I think probably you can put 2 to the s here, but 3 is certainly safe, right? So the idea is just roughly speaking, if you take this graph which has some number s of surplus edges, each time you remove a surplus edge, you sort of roughly can, in the worst case, double the diameter. So when you remove S surplus edges, you shouldn't make the surplus go up by more than a factor of about 2 to the S. Okay, so that implies that if we look at the diameter of this component of the minimum spanning forest, T naught, right, the largest tree in the spanning forest at criticality, that's almost 2 to the surplus of H, or 3 to the surplus, I guess I'm using 3 here, of H naught times the diameter of H naught. Okay, but we know that that this surplus, we've seen that this surplus is order 1 in probability, and we've seen that the diameter of a component of bounded surplus is of order square root of its size in probability. Okay, which is sorry, there should be a square root there, right? And these critical components have size of order n to the 2/3. So this is order n to the 3rd in probability. So here we have an upper bound, which is, something of order n to the 3rd times something of order 1. And so overall we get an upper bound of order n to the 3rd, just on the component of, just on the diameter of this particular tree. Right, so that doesn't give us a bound on the diameter of the whole, upper bound on the diameter of the whole minimum spanning tree, because this is, this inclusion goes the wrong way. We're going to have to work harder to get a bound on the whole minimum spanning tree. But it's at least a first step. Okay, and we can actually do a little bit better than just looking at the diameter at epsilon equals 0, because we learned a little bit, we learned about the sort of structure of the critical random graph, not just at 1 over n, but in a window around 1 over n, where we took epsilon to be the form constant over n to the 3rd. Then we saw this picture of the excursions as coded by a reflected Brownian motion, which was telling us that, in fact, the largest components stay of order n to the 1/3 all throughout that window. Okay, so so we can extend this result a little bit. We can in fact prove that for any constant in R, then if we look at the diameter of the tree T C over n to the 3rd, right? So this is the, just to reinforce, this is the minimum spanning tree of H C over n to the 3rd, which is the largest component of Gn 1 plus C on n to the 3rd over n. Okay, so the diameter of this subtree of the eventual MST is also of order n to the 3rd in probability. Okay, and the proof of that is no different from the proof that that we just did, because for any C, so we just did the proof in the case C is 0, but for any C in this range, if epsilon is C on n to the 3rd, then we know that the diameter of H epsilon is of order the square root of its size. So that's still of order n to the 3rd. And the surplus of H epsilon is still of order 1. Okay, and so so this bound that the diameter of T epsilon is at most 3 to the surplus of H epsilon times the diameter of H epsilon. Gives this upper bound here. This term is order 1 in probability, and this term is order n to the 3rd in probability. Okay, so the quality of this bound, I'm hiding, there's a dependence on C in this bound, right? It's not the case that for any C, the diameter is sort of uniformly of order, the size of this component is uniformly of order n to the 2/3. We know that if C tends to infinity, then the size of the largest component starts to be larger than n to the 2/3. Okay, but for any fixed C in this range, we have this bound. And so then the hope is that we can use this to get from, we'll try to start at some large constant c and somehow show that after that large time, the diameter shouldn't increase, or that large value, the diameter shouldn't increase very much. So the strategy then, strategy now is going to be to, well, we'll proceed in 2 steps. So one is to bound the difference between what happens at, so we know we can get up to epsilon, a sort of large constant over n to the third. So we'll try to get from there all the way up to epsilon, just a small constant. So t k over n to the third. So so for some k large, right? So this is going from, this corresponds to the, this is the largest, the tree in the forest corresponding to, so fn, and then p is 1 plus k on n to the third over n. And here we're all the way up at fn 1 plus 1 over k on n. Okay, so here we're still within the critical window, though almost at the end of it. And here we're practically at 1 plus constant over n, right? It's a small constant, but constant over n. Okay, so we'll do, that'll be one step. That's actually going to be the sort of harder step. And then the second step, which is easier and I'll actually do first, is to figure out what happens when we go from, this barely supercritical range all the way up to the final MST. So the difference between the minimum diameter of the minimum spanning tree and the diameter of T 1 over K. Okay, so is the sort of picture of the proof clear? Any questions? Okay, so this is what we're aiming for. We want to sort of grow from, thinking of the probability as time, then we're trying to sort of watch the process over time, saying we know that the process hasn't grown a tree of diameter bigger than n to the third at this time. Now we need to watch for the remainder of time and see that the diameter doesn't increase beyond that threshold that we're aiming for. Okay, so let's do this. What I said, this second step first. So that's proving an upper bound on the diameter of the minimum spanning tree minus the diameter of T epsilon. And here I'm thinking now of, so epsilon is my 1 over K. So that's for epsilon fixed. And you can think of it as small. Okay. So I'll show you that, so for this, in this regime, so for epsilon fixed, this difference here is in fact polylogarithmically small. So this is at most log squared n. Okay, so that's our target. And we're going to prove this by analyzing a sort of variant of PIMS algorithm. Okay, so I want to think about conditioning on the graph. I'm interested in understanding the diameter increase between time t epsilon. So here we're sort of sitting in fn 1 plus epsilon over n, or gn 1 plus epsilon over n. And so what happens after this time going up to time 1? So I want to condition on the structure at this time, okay? And then do my analysis conditional on the structure. So let's write, let me sort of, well, let me write that down. So we're going to condition on gn 1 plus epsilon over n, and then run PIMS algorithm from an arbitrary starting vertex. So Okay, so the picture to have in mind, now we're sitting in this sort of supercritical random graph, is that the largest component, remember we called that H epsilon, is occupying some large macroscopic section of the graph. Okay, so the size of, we think that the size of this H epsilon should be, roughly like n times theta of 1 plus epsilon, right? So some potentially small but constant proportion of the graph. And then the other components of this graph are all sort of quite small pieces. There's just some sort of dust hanging out over here. Okay, and then sitting inside of this, there's some minimum spanning trees, if you like, the forest F on each of these. Okay, so this is the kind of schematic picture of the graph at this point. Okay, and what I'd like to do is say, I can bound the increase in the diameter between time epsilon and the final graph by thinking about, well, if Prim's algorithm, hops through 5 components before it gets to the giant component, then that builds a path, and the longest possible length of that path is 5 times the largest, whatever the largest size of any of these components is. If none of the components it goes through has size bigger than 100 and it only makes 5 steps, then 5 times 100 is an upper bound on the diameter increase, sort of due to that particular path. So if I can just show that no matter where Prim's algorithm starts, it's not very likely to build a very long path, then I can use that as an overall diameter bound on the diameter increase. Okay, so let me to formalize that, let me write JV for the number of components that Prim's algorithm goes through if we start at vertex V until it gets to H epsilon. Okay, so this is the number of components of F and 1 plus epsilon on n visited by Prim's algorithm, starting from V and before visiting or before reaching T epsilon. Right, this spanning tree of H epsilon over here is T epsilon. Right? So then I can bound, with that definition, I can bound the difference that I'm trying to bound by, so the largest of these JV plus 1 times the largest size of any component other than the giant. So the largest size of C, such that so C is a component of G and 1 plus epsilon over n, which is different from the largest component. Right, so where does this bound come from? This is just because if I take any path, from, the diameter, I guess I need a 2 in front of this. So the point is that how can the diameter, how different from the diameter of this graph can the diameter of the whole graph be? Well, in the worst case, a path, the diameter could be increased because now we could build some path which jumps through some components of some of these small components. Then it joins itself into the largest component. Okay, then it follows some path in the largest component, and then it leaves and creates another path outside of the largest component. Okay, so each of these paths, could in principle, well, I'm adding this +1 for each of these sort of connective edges, but maybe there's actually a -1 from the interior. The point is that, you know, if I bound the length of sort of traveling through a component plus leaving the component by the largest size of a component +1, then that gives me then sort of this term counts the contribution from any route through a component plus leaving, and then oh, sorry. No, I said that wrong. This is here. I'm counting the largest size of any of these components. So the length of a path that goes through a component and then leaves is at most this term here. Okay, because you know, if a component has 10 vertices, then a path through it has at most 9 edges plus the edge that you leave by. Gives you, you know, at most a contribution of 10 edges from a component with 10 vertices. So each component like this, so each component gives you a contribution which is at most this largest size of any non-giant component. And the number of those you can get is at most sort of, well, some number starting from one end here, some number leaving from the other end there, and an upper bound on each of those is this number, the number of components visited by Prim's algorithm before you reach the final graph. Okay, and so maybe I don't even need this this +1 here. Okay, so what I'd like to do now, right? So the goal is to prove that after time h epsilon, the diameter increase is at most log squared n. So I can just show you that each of these terms is at most order log n in probability, and that will give me my upper bound. Okay, so so the proposition follows if, you know, let me call this 1 and this 2, if 1 and 2 are both order log n in probability. Okay, well, we've already seen one of those facts. You know, we already saw that the largest non-giant component is order log n in probability. Right, I showed you a weaker bound first, but then we said that by sort of comparison with a subcritical branching process, all the components of all the non-giant components of a supercritical random graph actually look subcritical. Okay, so this is you know, that's known from our study of the Addario-Berry random graph, right? And maybe I'll say a little bit more about that because I'm going to kind of I'm going to use this sort of thing in a bit more detail later. Okay, so you know, more precisely, you know, we saw that after exploring h epsilon, what remains looks like, you know, g n prime 1 plus epsilon over n, where n prime is like n times 1 minus theta of 1 plus epsilon. And this graph looks roughly like, so if you sort of rewrite this probability in terms of n prime, and let me just write lambda for the moment as 1 plus epsilon, then this looks like gn prime lambda hat over n prime, where lambda hat is the dual parameter to lambda, and this is a subcritical random graph. Okay, so that's sort of one way to see that that the other components are all logarithmic in size. Okay, and so I want to, you know, really focus on this first term. So then it, you know, given that, it remains to to show that, so we want this quantity here to be order log n in probability. Okay, and remember, so J, what's J again? J is the number of hops. So if you sort of run PIMS algorithm, but you only count the steps which go between components before you reach H epsilon, J is the number of such hops, right? And then we're maximizing that over all components. Okay, so let's analyze that now, right? So let's think about what happens when we add an edge that's not within one of these components. So remember, I'm going to I'm thinking of fixing, fixing the structure of this graph here, and then running PIMS algorithm, right? Well, starting from, in this example that I've just drawn, where the component containing V is just a vertex, right? So the first edge that it adds is the smallest weight edge leaving V. It's uniformly random among all, the smallest weight edge is uniformly random over the whole graph, right? And so so the probability that it hits H epsilon is just the size of H epsilon over n minus 1. Okay, so that's the first step. Maybe we don't get lucky. V goes over here and does some exploration. Okay. Well, now at some point we know in fact what we'll explore. We'll exhaust the exploration of the spanning tree of this component, and then we'll add an edge to the rest of the graph. Okay. Now where will that next edge go? Well, in this, it's not going to go to V. V's already been spanned, so it has probability, size of H epsilon over everything that's left of connecting to H epsilon. Okay. And if we don't get lucky again, then maybe we we add an edge over here and explore this component. And now we when we have exhausted that, we have to leave this component. And at every step, right, all that we know. Well, maybe there's something more to say here. It's at this moment in principle, PIMS algorithm adds the smallest weight edge that's available to it. So the edge is not equally likely to emanate from any of these vertices, right? When we added this edge, it was the smallest weight edge leaving V. So if it had weight, if we were really unlucky and it had weight 1/2, then now we know that all of the other edges leaving V have weight bigger than 1/2. Okay, and so if there's if all we know about the edges leaving here is that they're at most 1 plus epsilon over n, then it's far more likely that the next edge leaving the exploration leaves from this component rather than leaving from V. And more generally, whatever's added earlier by PIMS algorithm, we learn more about the edge weights leaving that section. So when this edge was added, it was the smallest weight edge leaving all of this section. So now we know that all of the edges leaving this section of the exploration are bigger than the weight of this edge, whereas we don't have such information about this component. So the next edge, after we explore these 3 components, the next edge is more likely to leave from here than it is from back here. Okay, but where it goes it continues to be uniformly random. We don't have any information about the stuff that's outside of what we've explored so far. So no matter where we leave from, where we leave to is a uniformly random vertex of what's left. That's the key point. Okay, so each time we finish exploring a component, we have chance size of H epsilon over whatever size is left of joining up to H epsilon. Okay, so let me write that down. I think I've explained it in words enough now. So each time PIMS algorithm adds an edge not in Fn 1 plus epsilon on n, it has probability at least, so H epsilon over n minus 1 of connecting to T epsilon, if it hasn't already. Okay, and that's just because although where it connects from might not be uniformly random over the tree that's built so far, where it connects to is always uniformly random over what remains to be connected. Okay, so that means that if we condition on the structure of fn1 plus epsilon, or of gn1 plus epsilon, so conditionally given gn1 plus epsilon on n, the number of hops we have to do until we hit this big component. Well, at each hop we have success probability bigger than h epsilon on n of succeeding. So that number of hops, JV, is stochastically dominated by a geometric random variable with success probability h epsilon divided by n. Okay, but now since we know that the size of h epsilon is like well, we proved a law of large numbers for that. It's n theta of 1 plus epsilon. Then this upper bound, this is basically like, well, n1 plus epsilon on n, so geometric with success probability theta of 1 plus epsilon. And we're thinking of epsilon as a constant, so this success probability is just a constant, right? So it's a geometric with constant parameter. So this upper bound is order 1 in probability. Okay, and so that means now that the probability that the largest of these is bigger than k log n. Using this, I'm going to use this stochastic relation now to bound the maximum and not just a single term. So I have to be a little bit more careful. Just because one of them is going to be order 1 doesn't mean the biggest is going to be of order 1, right? But I can say that that's at most, I want to argue conditionally on this structure. So the bad news is if h epsilon for some reason is much smaller than it should be, because then my geometric bound gets bad. Okay, so if I'm unlucky and the largest component is less than half of the size it should be, then I'll say that's bad news. But we know by the law of large numbers that's unlikely. And then in the good news situation, where that size is not too much smaller than it's supposed to be, so I'll write, for that term we bound this by the probability that the maximum is bigger than k log n, given that the giant has size bigger than half its expected value. Okay. And the first term is little o1 by the law of large numbers. And the second term is, so just by union bound, n times the probability that one of these terms is bigger than k log n, given this, which is just the probability that a geometric with success parameter theta 1 plus epsilon on 2 takes value bigger than k log n, right? So I'm just here using union bound over the vertices, and then for each vertex I'm using this stochastic domination to get this upper bound. Okay, so here I have n, that's a minus. I have n and then some constant less than 1 to constant log n. And so if k is large, then this whole thing tends to 0. Right, and so that shows that the maximum is indeed order log n in probability. Okay, so those are the two steps we needed. The number of hops isn't more than logarithmic, and each hop takes no more than a logarithmic number of steps. So we get an overall bound of log squared n on the diameter increase. Okay. Right. So that says, there's something interesting about. I mean, the proof of this isn't very hard once you sort of have the idea of using PIMS algorithm, but there is something that's worth remarking on here. This component here, epsilon can be as small as you like. So this component here can contain 1% of the vertices of the eventual spanning tree, right? But this result is telling you that it's already really determined the global geometric structure of the minimum spanning tree. All that's left is sort of addition of mass onto it. It's not about, which doesn't really change its geometry. This thing is going to have, we know that this thing has a diameter of at least order n to the third, and now we're adding on some paths of polylogarithmic length. That really doesn't change the metric picture very much, only the measured picture if you think about the vertex additions as adding mass, as changing the measure of the thing. Okay, so that's the first of two steps. Okay, well, the second of three, if you like. I mean, the first one was to say that at time constant over n to the third, the diameter was still order n to the third. Now we've said that once the time is some small positive constant, the diameter doesn't change very much. And now we need to go between those two steps. And that's what the rest of the lecture will be about. Okay. So, we're going to, at a high level, what we're going to do is sort of go through that, break that jump from constant over n to the third to small positive constant up into pieces, and bound the diameter increase on each of those pieces and show that that the bounds are, so we'll prove bounds that are geometrically decaying so that they're summable. That's the plan. Okay, but the way that we're gonna to do that is by stepping through so increasing time in increments so that in each increase some new pieces will get glued on. Okay, and then that will cause the giant component to look even bigger, and what's left to look even smaller. And so that's the fact that each time new stuff gets glued on, it makes the giant look more supercritical, and what's left look more subcritical. Is why you can hope for a sort of geometric bound. Okay, so I'll get to sort of to formalizing how we step through in just a sec. But there's sort of one more. There's sort of, because we need to control the diameter increase when these new pieces glue on, and the new pieces that are gluing on are always coming from what sort of looks like a subcritical graph. It's the part of this supercritical graph after you remove the giant. I just need to state a fact about the behavior of diameters in subcritical facts, which is sort of a slight extension of what we saw in the in studying random graphs, but it shouldn't feel too unfamiliar given what we've already seen. So I'll give you a sort of proof sketch of this, not full details, but I think that it should be convincing given what we've seen already. So this is a sort of preparatory fact for that step A of that remains in the proof. So we're looking at the setting where so epsilon over n to the third tends to infinity, and epsilon is less than 1, and I'm looking at a subcritical graph. So in Gn 1 minus epsilon on n, then with high probability, so with probability tending to 1, two things happen. One is that, so the largest component of, the largest diameter of any component is at most order, so log of epsilon cubed n over epsilon. And the second fact is that the largest surplus of any component is not order 1, is at most 1 with high probability. Okay. So I guess I can move this line here. So the first line, there's no need for with high probability because the probability is sort of encapsulated in this notation. Okay. So we're saying there's no component of bigger than of diameter bigger than this polylog factor over epsilon, and there's no component with more than one surplus edge in a subcritical random graph. Okay, so let me explain why these are true. So the step that I won't sort of do in full detail, but I'll use multiple times, is that so a component of diameter about k has size about k squared. So this is somehow using that these components roughly have like quadratic volume growth, like random trees do. Okay, so we've seen we've never precisely proved this, but we've seen various facts that are closely related to this, and I'll sort of lean fairly heavily on this throughout the proof. I mean, to the point where I'll say I'll use as though it's equivalent in terms of events, that if a component has size about s, then or size about m, then its diameter will be about square root of m. Okay, so you have I mean, the fact that those two things aren't literally equivalent, they just are typically equivalent, makes turning what I write into an actual proof a little bit more delicate, because you have to control the errors in that sort of events that I'm describing. But if you're willing to sort of believe the story that these two things are roughly equivalent, then you can get the intuition for why the fact is true quite easily. Okay, so we're focusing now in this graph gn1 minus epsilon over n. So what's the probability that the diameter of a component is bigger than k? So right away we'll use this sort of heuristic that we didn't prove. Say this is roughly the probability that the component has size bigger than k squared. Okay, and now just using the coupling with Poisson bien-aimé, we know that that's like at most the probability that a Poisson 1 minus epsilon bien-aimé tree has size bigger than k squared. Okay, and so we've seen a bound on this term, but let me use that in a second. Let me for the moment just treat this as a bound, use it to derive a bound on the expected number of components of large diameter, and then use our what we know about how these probabilities decay. So that tells me the expected number of components of diameter bigger than k. Well, if each such component has about k squared vertices, then the number of components of this size is about k squared smaller, or sorry, the number of components of this diameter is about a factor k squared smaller than the number of vertices in those components, because each component will have about k squared vertices. Okay, so this is at most roughly 1 over k squared times the expected number of vertices that are in components of size bigger than k squared. Okay, and now our bound says that that's at most roughly, so linearity of expectation n over k squared times the probability that one vertex is in such a large component. Okay. So now what do we know about this bound on the right? Well, we saw that the probability that that a subcritical bien-aimé tree like this has size bigger than x on epsilon squared was like order 1 on x on epsilon squared to the half e to the minus x on 2. Okay, just using Stirling's formula basically, and then approximating the sum by a Riemann integral, right? And so then if we take k to be this x on epsilon squared to the half, okay, then this tells us that so the expected number of components, there should be a number in there. So the expected number of components of diameter bigger than x on epsilon squared. This is a k and not a k squared. So diameter x on epsilon squared to the half, which is what? X to the half on epsilon is, so order 1, then we have n over k squared, so x on epsilon squared, and then we have this this upper bound here. So that gives us an extra x on epsilon squared to the half, and then e to the minus x on 2. So let me just rearrange that. Here we have a 1 on epsilon cubed on the bottom, so that's n epsilon cubed over x to the half e to the minus x on 2 with an order 1. Okay, so up to this heuristic that having diameter bigger than k is roughly the same as having size bigger than k squared, we've derived a upper bound on the expected number of components of diameter bigger than sort of something over epsilon. And what do we have to do over here to get a good bound? We need to cancel this n epsilon cubed, right? So taking x to be like a log of order log n epsilon cubed is precisely what's needed to get a small bound here. Okay, and that's what that's the sort of upper bound we stated. So we have the one on epsilon here, and then we have to take x large enough to cancel this, so that this here is like little o1. So maybe I could even have written a half right there. I think I could have, but I don't need better than this. Okay, so that's the first. That's the sort of intuition for the first step. For the second, the ideas are sort of similar. They're maybe a little bit easier, but let me go through it. So we're going to continue to use the bound on so the upper bound on a component size, but we don't need this. This is just a statement about surplus and not about diameter. So we don't need this heuristic anymore. Okay, but I will use a slightly different heuristic, which is that so I'll use that a component of size k has surplus, which is roughly like a binomial k to the 3 halves 1 over n, or roughly a Poisson k to the 3 halves over n. Okay, and this is, I owe you an explanation of this as well. The rough idea is what comes from the exploration process perspective on these components, right? We saw that, so when you explore a component, you have this queue of active vertices, right? And at any given time, at any given step, there are some edges that you could add or leave out, which are the surplus edges, which don't change the sort of depth first search tree that you build. Okay, and the discrete area under this curve is precisely the number of potential locations for surplus edges, right? So when we build a tree T, the potential number of surplus edges was the area under the excursion for T, which we sort of wrote area of T, and this statement here is really just that this area is roughly the size of T to the 3 halves, because this excursion looks roughly like a random walk. So if it has length k, then it will have sort of typical height of order square root k. Okay, so when this length is k, then the sort of typical height of the excursion is k to the half. So the total area under the excursion will be like k to the 3 halves, and that's telling you the number of possible places for surplus edges. And each of those shows up with probability about 1 over n. Okay, so in particular, if k to the 3/2 over n is much smaller than 1, then the probability that a component of size k has surplus at least 2, well, this is now roughly like the probability that a Poisson k to the 3/2 on n is at least 2, which is, well, the easiest way, if this parameter is small, then this is the easiest way to have value at least 2 is to have value exactly 2, and that probability is like just the parameter squared. So the probability that Poisson k to the 3/2 on n is equal to 2, which is what, a half k to the 3/2 on n squared. Okay, so that's so it's just this order of magnitude for the probability that a component of size k has surplus at least 2 that I'm going to use now. Okay, so let's just use that to do a sort of rough calculation of the expected number of components of, let's say, size in some interval, some dyadic interval k2k, and surplus bigger than 1. Okay, well, again, so for each component of, I can count components, or I can count vertices in those components, and there's a factor k, or between k and 2k, that relates them. So that's roughly like 1 over k times the expected number of vertices that have component size between k and 2k, and surplus bigger than 1. Okay, and now, so that's like at most like n over k, and using our Poisson bound again, times the probability that Poisson 1 minus epsilon bien Ametri has size say greater than or equal to k. Okay, and let's just bound this by 1 on k to the half. And sorry, and then we still need times the probability that this Poisson k to the 3/2 on n is bigger than 1. Okay, so I'm just saying, so the n here comes from linearity of expectation to focus on a single vertex rather than all n vertices, and then I'm saying, if one vertex is going to have the probability one vertex has this size, we can bound by what the component of a single vertex has this size, we can bound by this probability, and then given that it has this size, the probability its surplus is bigger than 1, we bound using the argument we just saw. Okay, so this probability is at most like 1 on k to the half. That's we can even put 1 instead of 1 minus epsilon here, and that's still true. Okay, and now for this probability, we have a k to the 3/2 on n all squared, and so this term, well, one of these two terms cancels with this term, and so the whole bound we get is like k to the 3/2 on n. Okay, so this is a good bound if k to the 3/2 is much smaller than n, right? But now we know that in when what regime are we were focused on? We're in the subcritical regime. Okay, so the largest component size here is little o of n to the 2/3. So we only have to look at components of size much smaller than n to the 2/3 in order to prove the fact, because there are no bigger components. Okay, so now if we just, so now we can sum this bound. Well, what's in this regime, we know that the largest component, so the largest component overall has size at most. So the bound we saw was log epsilon cubed n over epsilon squared, which is little o of n to the 2/3. Okay, so now you can sum this bound over. So the reason we did these dyadic intervals is so that we can sum it over k of the form 2 to the I, where 2 to the I is now at most our bound here. Okay, and so even at the very largest value of k here, the contribution here is a little o of 1. Okay, and then as k decreases from the maximal value, the expected number geometrically decreases. So the sum overall is little o of 1. Okay. So the total expected number of components of surplus greater than 1 is little o 1. Okay, so that's I hope that step might have felt a little bit hasty, but the method here is really fairly straightforward. You just are well, I mean, up to this heuristic, which again is a step that needs a little bit of justification. But if you sort of believe this approximation here, then the rest is really follows quite straightforwardly. Okay, so this is the input we need about subcritical random graphs. We want to know that the diameter of the pieces is small because these pieces are going to get glued on, and we don't want them to aggregate to increase the overall diameter very much as we increase through the critical window. Okay, and we want to know their surplus is small because the diameter of the component doesn't have to be the same as the diameter of its spanning tree, and we have a good bound on that as long as the surplus is small. So we actually got that the surplus is at most 1, so we get a very good relation. I mean, the diameter of the tree is sort of not more than double the diameter of the component. Okay, so now I think we have the pieces we need, and I'll move to this step A here. Okay, so I have a sort of key lemma, which is the thing that allows us to do one step of the. I said we're going to split this increase up into steps, and this lemma is what we'll use to bound the increase in diameter at each step. Okay, so given a graph G, I'll write LP of G for the longest, the length of the longest path in G. So okay, so this can be even longer than the diameter. It's just the long. You're allowed. It doesn't have to be a geodesic of any kind. You can take any path you like. And now we'll look at graphs G and G prime. So connected graphs with the same vertex set, but so G is a subgraph of G prime. Okay, and I'll look at, actually, so these don't need to be connected, just graphs. Now I'll look at connected components of these graphs. So H and H prime be connected components of G and G prime. Okay, then I can bound the diameter of H prime from above by the diameter of H plus twice the length of the longest path in the subgraph of G prime that I get by restricting to the vertices outside of H, plus 1. Okay, so this notation, I don't know if you're familiar with this notation. So when I write G of a set S, this means the subgraph of G induced by the vertex set S. So it says you take this is a subset of the vertices, and you just take that subset of the vertices and all the edges. Okay, so so this lemma, I think this lemma becomes easier to parse if I just show you the sort of picture of what's going on. Right. So here's the picture. This is the graph G prime, this blob here. It has the same vertex set as G. And now H is a component of G, H prime is a component of G prime. And we're trying to bound the diameter of H prime in terms of the diameter of H plus the longest path in what's left if you remove H from this picture. Okay. So let's just think about how you could build, well, how much the diameter of could increase when you move from H to H prime. Okay, so if we're given vertices U1 and U2 in H prime, okay, so here's U1 and here's U2. Well, one way that we could build a path from U1 to U2, right? If we're trying to bound the diameter of H prime from above, it suffices to bound the length of the shortest path between any two vertices in H prime from above, because the diameter is just the longest such length, right? So I'll do that by just thinking about taking a path from U1 to H and a path from U2 to H, and then joining them up within H. Okay, so let's let, so P be a shortest path from U1 to H, and I'll call its other end V1. Okay. And then, so let's let Q be a shortest path from U2 to H, and I'll call its other end V2. The longest, there's a question, is LP the longest simple path? Yes, the longest simple path. You're not allowed to just go around and around and around a cycle. Right, so here's the path. So this is P, and this is Q. And then I'll let R be a shortest path from V1 to V2 in H. Okay, so here's R. Okay. Now, if I call, that's not a very legible P. If I call this quantity in the bound here L, right, then P has length at most L because it's some shortest path to H. So in particular, if I exclude its final edge, then it is some path in H prime minus H. So it's some path in this graph, right? The graph I get from G prime by excluding H. And so its length is at most the length of the longest path in that graph. And then I have to add 1 for the edge going into H. And likewise, this is some path in G prime when you remove H. So its length is at most the longest path in there. And then I add 1. Okay, so then the length of P is at most L, and the length of Q is at most L. And the length of R, well, R is the shortest path between two vertices in H, so its length is at most the diameter of H. Right? So when I put them together, we get that the distance in h prime between u1 and u2 is at most the diameter of h plus 2l. Okay, and since that's true for any vertices in h prime, it follows that the diameter of h prime is at most the diameter of h plus 2l, which is the upper bound we were trying to prove. Okay. So this says that we can, so, you know, the names G and G prime and H prime are strategic. You know, we're going to be applying this where H is the largest component of in the Addario-Berry process, or really its minimum spanning tree. And then H prime is what is the component you get after you've increased the parameter P a little bit. Okay, and so that's how we're going to bound the increase. Okay, so here's the proposition that's going to follow from that key lemma. So if we take some epsilon tending to 0, such that epsilon over n to the third tends to infinity, then the diameter of t, so 3 epsilon over 2, minus the diameter, well, let me write it the same way as in the lemma, is at most the diameter of t epsilon plus order log epsilon cubed n over epsilon. Okay, so we're really thinking about, you know, here's our h prime, if you like, here's our h, and then this error term is supposed to come from bounding the longest paths in what's outside. Okay, so and this 3 epsilon over 2, from epsilon to 3 epsilon over 2, tells you how it is that we're going to step through the window that's left to cover between epsilon, you know, large constant n to the third, and epsilon just a small constant. We're going to step through in geometric increases where you multiply by a factor of 3/2 at each step. Okay, so the proof of this really, you know, boils down to facts about the Addario-Berry process plus this key lemma. So the key lemma tells us that, you know, as long as it's the case that h epsilon is contained in h 3 epsilon over 2, right, that the largest components are actually nested in this way, that's needed for the lemma. We have to be growing the largest component. As long as that happens, then the diameter that we're trying to bound, so at time 3 epsilon over 2, is at most the diameter of t epsilon plus twice the length of the longest path in a graph I'll call G. I'll just shorten it to G hat. What is this? No, first, maybe I'll do that in a second. So the graph we have to look at here is, so the graph Gn, so recall the notation, so G epsilon is Gn 1 plus epsilon over n. Okay, so the graph I have here is G 3 epsilon over 2, but then restricted to the vertices that aren't part of the giant component h epsilon. I have to remove them. And then I have to add 1. Okay, so that's the bound that the key lemma tells me. And I'd like to call this graph here G hat for the rest of the proof, because epsilon is going to be sort of fixed for now. I don't need to carry it. Sorry about that. Right. So maybe a little picture is in order. Okay. we've got our component H epsilon, right? We think about removing it, and now there are all these other components of. So these are other components of G epsilon, right? But then we increase epsilon, right? We increase the value p from 1 plus epsilon over n to 1 plus 3/2 epsilon over n. And so some new edges come along and join up some of these components over here. Okay? And the way we're bounding the increase of the increase in this diameter of T epsilon is to say, well, it's whatever we had before plus, you know, however long a path might have been built outside of H epsilon in the meantime when we increased from epsilon to 3 epsilon over 2. So we need to control what happens out here, not just after you remove H epsilon, but then also after you add some edges. And that's the only sort of subtlety to the proof. You know, the point is that we chose 3/2 here because it makes the picture outside of H epsilon still look subcritical. So these bits won't have sort of agglomerated into too big of a component. Okay, and so let me explain the reason for that. So we know that when epsilon over n to the third tends to infinity, and epsilon is little o of 1, then the size of H epsilon is like 2 plus little o 1 in probability times epsilon n, right? So if I write n prime for n minus 2 epsilon n, okay, so that's n times 1 minus 2 epsilon, then this graph g hat, right? G hat is, so the percolation parameter is this 1 plus 3 epsilon over 2 over n, but the size of the remaining graph is basically like n prime, right? Because we removed H epsilon, which has size basically 2 epsilon n. Okay, so G hat looks roughly like a random graph. So with n prime vertices and parameter 1 plus 3 epsilon over 2 divided by n. Okay, which I can rewrite just using the definition of n prime as so 1 plus 3 epsilon on 2 times 1 minus 2 epsilon all divided by n prime. Okay, so here I'm using this deterministic size n prime as a proxy for the size of H epsilon, and I'm going to be a little bit casual about that. You know, in principle, I need to say that with high probability, H epsilon really has this behavior, but we sort of already saw the law of large numbers for this. So I'm just going to, you know, behave as though H epsilon behaves and really has size n prime for explaining how this diameter increase bound comes about. Okay, so let's work out what this parameter here looks like now for the remaining graph g hat, right? Well, we have 1 plus 3 epsilon on 2, and then 1 minus 2 epsilon. So that looks like 1 minus epsilon on 2 plus 3/4 epsilon squared. Okay, so the dominant term when epsilon is small is 1 minus epsilon on 2. And if, you know, certainly if n is large, then this, and epsilon is tending to 0, then, you know, this is at most 1 minus epsilon on 4, say. Okay, so the point is that what's left out here, even after we add these yellow edges, the edges that take us from epsilon to 3 epsilon over 2, still looks like a subcritical random graph. Okay, it's not quite as subcritical. We got an epsilon over 4 out instead of an epsilon, but it's subcritical. Okay, so now in the graph, you know, in a graph gn 1 minus epsilon over n, we know that the largest component size, so we have size of C max is order log epsilon cubed n on epsilon squared, which is in particular little o of epsilon n. Okay, we saw that before. And so that tells us that with high probability, well, actually, I don't need more information about the size. I need information about the diameter. We just proved that in a graph like this, we have a diameter bound order log epsilon cubed n over epsilon, and surplus at most 1 with high probability, right? And so that means that the longest path in G hat, which looks like the longest path in this graph G, so n prime 1 minus epsilon over 4 over n prime, right? Well, I'm being generous here. Really, it's closer to 1 minus epsilon over 2, but I'm only looking for an upper bound. So so this longest path is sort of at most stochastically about the longest path in here. This looks like order log epsilon cubed n over epsilon, right? I mean, so I need a bound on the longest path and not the diameter. But if the surplus is at most 1, then the diameter is at most, the length of the longest path is at most twice the diameter. You can't sort of use each, there's, you have to, you can use this one extra edge, and then you have 2 paths which were paths in the original tree, each of which then has length at most the diameter of the tree. Okay. And so that tells me that, right, so let's back up. Where are we now? We've said that when the largest components are nested like this, we got an upper bound which was precisely of the form that we wanted, right? We said that this difference should be order log epsilon cubed n on epsilon, and that's precisely what we got for the longest path. Okay. But now, the event that we needed to happen has probability tending to 1, right? When epsilon over n to the third tends to infinity, the largest components really are nested like this. So since so h epsilon is the subgraph of h 3 epsilon over 2 with high probability, the proposition follows. Okay, so so we've shown that we've shown a bound on how much the diameter increases when we go from epsilon to 3 epsilon over 2, and note that the bound gets better as epsilon gets bigger, right? Because it's something with a log epsilon on the top and an epsilon on the bottom. Okay. So now we'll use that to finish this step A of bounding the diameter increase when we go from constant over n to the third to 1 over constant. Maybe just before I do that, let me mention, so this fact here, there's actually a stronger version of this known. So it's in fact, if you look at the probability that, so h epsilon, so that the giant, so once the leader, once this largest component emerges out of the critical window, its identity never changes. So the probability that h epsilon is contained in h epsilon prime for all, epsilon less than epsilon prime with, so let me write it this way. So for if epsilon over n to the third tends to infinity, then the probability that after time epsilon, these largest components are always nested from then on forever, and this tends to 1. Okay, so this is sometimes called the leader phenomenon. So once a leader emerges, it never changes. Okay, I didn't really use that in the proof of the proposition, but it's a nice fact. I thought I'd mention this is due to Thomas Wuczak from 1990. Okay, so now having proved that, I think we can sort of do the finishing stroke. So I want to prove that if we have a function omega n, which tends to infinity arbitrarily slowly, then the diameter of t1 on omega n minus the diameter of t at time omega n on n to the third is little o n to the third in probability. Okay, and this really finishes the step A. It gets you from large constant over n to the third to small constant. Okay, so to prove this, we'll just take a sequence now of steps. So let epsilon I be 3/2 to the I times the starting value omega n over n to the third. Okay, and how many steps do we need? Well, log base 3/2 n to the third over omega squared, because that's the ratio of these two terms. Okay, then epsilon, the last epsilon is somewhere between 1 on omega n and 3/2 1 on omega n, right? So it's basically where we're targeting here. Okay, so then if h epsilon is contained in h epsilon prime for all epsilon prime bigger than omega over n to the third here, right? So now I guess I am using this stronger fact that this happens for all of these values, right? Then the diameter difference between these times, so this difference that we're trying to bound, is going to be at most, so the sum from 1 to k of diameter of t at time epsilon I minus the diameter at time epsilon I minus 1, okay, which we now know is at most, sum for I from 1 to k of log of epsilon I cubed n over epsilon I. Okay, so here is one more step where I'm being a little bit uncautious, right? Because I've just, I have a bound for each of these sum ends. I have a bound of this form, okay? So, and this order p log epsilon cubed n over epsilon. Okay, so I know that each of these sum ends individually is unlikely to be, much bigger than this order. But there's more than a constant number of sum ends, right? So in theory, even if each one individually is unlikely to display some big, some big fluctuation above this value, it might be that when you get lots of them, one of them is actually likely to fluctuate. So there's a non-trivial step. I'm not going to do that step, but there's a non-trivial step to, actually prove tail bounds on these error probabilities, which are good enough that you can really take this order outside of the summation. Okay, so that's there's a sort of warning there that to make this fully rigorous, you need more quantitative control than I've showed you. Okay, but if you're willing to accept that, our bounds on the diameter increase can be combined in this way, then this gives us overall a bound just using the definition of the epsilon I, right? 3/2 to the I omega n over n to the third, which is like n to the third and then sum from 1 to k of log of 3/2 to the I omega n over 3/2 to the I omega n. Okay, and these summands are geometrically decreasing, so they're dominated by their first term, which is already sort of order log log omega n over omega n. So this is order n to the third log omega n over omega n, and since omega is tending to infinity, that's little o of n to the third. Okay, so I mean, really all that we're doing is stepping through the critical window in these steps, multiplicative steps of order 3/2. And this 3/2 was just chosen less than 2 in order that when you aggregate, what was outside with these extra edges, you're still left with something that looks subcritical enough that the diameter keeps going down. Okay, so that's really the whole idea of the proof. And then, so in this proposition, rather than taking a small constant here and a large constant here, I took something tending to 0 here and tending to infinity here. But really that immediately implies the version with, where you only want an order p in probability bound for n to the third. So if, I'll just state that as a corollary. So, this implies that for any delta greater than 0, there's k such that the probability that T1 over k has diameter, so the difference in diameter between time 1 over k and time k over n to the third is bigger than delta n to the third is less than delta. Okay, and the proof is just a very soft argument, right? If this failed, then you could extract a subsequence of values, so k tending to infinity, where you kept having uniformly positive probability of seeing sort of positive constant n to the third difference between these two quantities, and the proposition rules that out. So if not, then taking subsequences contradicts the proposition. Okay, so we've now seen that, we've now seen all the pieces. We saw that the diameter at time k over n to the third is order n to the third, right? We saw that the diameter at time 1 over k is at most order n to the third bigger than it was at time k over n to the third. Right, and then the last piece was using Prim's algorithm. We saw that the diameter of the minimum spanning tree minus the diameter at time 1 over k is in fact much smaller, order log squared n, right? And so just telescoping these together gives the bound that we were aiming for. Okay, so if you want to, I'm just going to say 1 or 2 more words before wrapping up. I know I'm at time already. So this, this controls the diameter of, this was our upper bound to match the lower bound, okay? We now know the diameter is typically of order n to the third, If you want to get your hands on the structure of this tree in more detail, this also told us that effectively, we now know that in some sense, the minimum spanning tree is roughly structured like the tree T at time large constant over n to the third. Okay. So you could think about trying to understand this tree directly to get a better handle on the structure of the minimum spanning tree. Okay. And one way to do that is to take this is the minimum spanning tree of the largest component, h, k over n to the third. Okay. And these large components, we actually understood their structure. They look like these kernels, these random 3 regular graphs, okay, with random edge lengths, and then with some sort of decorations. Okay. And if you start to think about the minimum spanning tree of this object, it actually really is the best or the only way I know to understand the kind of structure of the minimum spanning tree in finer detail. And the way you do that is using the cycle breaking algorithm that we saw. So starting from this picture, you can imagine starting to remove large weight edges rather than add small weight edges. Okay? And you only remove edges if they break cycles in the cycle breaking process. And so we'll only actually remove edges that lie on this core that we built. Okay? And then the nice distributional properties of the core that we sort of saw, that these edge lengths are exchangeable and we have sort of explicit distributional descriptions, allow you to kind of get your hands on the behavior of cycle breaking on this graph, and so understand the minimum spanning tree in more detail. Okay, and in some sense, it actually tells you, if you think about that the complete graph is not the sort of single most natural object to study the minimum spanning tree on. In a way, the most natural object to study the minimum spanning tree on in the mean field is a random 3 regular graph rather than a complete graph. And not even just a random 3 regular graph, but a random 3 regular graph with random edge lengths corresponding to this core. Because if you do that, then there's a self-similarity. When you get an object where if you take this graph and kind of do critical percolation on it, you get another object of the same kind, just a smaller version. And that self-similarity can actually be bootstrapped to prove that the minimum spanning tree of a random 3 regular graph looks sort of the same as the minimum spanning tree of a complete graph. So we've used that approach in some other work. Okay, so that's about all I'm going to say on global structure, but I think I've given you a sort of pretty good idea of how one approaches the global structure. There's still lots of models where it would be nice to know that this same story works, where we don't. But I won't talk about those. I'm going to focus in on the local structure for Thursday and Friday, describe the local limit of the minimum spanning tree, and prove the law of large numbers for the total weight of the minimum spanning tree. Thanks.